Okay, good morning. So last lecture we talked about bubble sort. In the previous lectures we talked about searching algorithms. Um, so today we're going to move to another notion, and I'm going to motivate this with an example. So call this section growth of functions. Okay. All right. So suppose. Algorithm A uses 100 times n squared plus 17n plus 4 operations, and algorithm B uses n cubed operations. On a given input list with n elements. Okay? All right, so if you give algorithm A and algorithm B a list with n elements, there's some problem that they're solving on this list, and the first algorithm uses this many operations, and the second algorithm uses n cubed operations. Okay, so the question is, so which algorithm is better in terms of computation, right? So which one is going to be faster? Well, in order to measure the efficiencies of these algorithms, we're going to introduce something called big O. So big O notation is used extensively to estimate the number of operations an algorithm uses. Okay, so this notation that we're going to introduce is going to, in a sense, give some type of interpretation behind what it means to use that many operations versus what it means to use this many operations. Okay, so that leads us to the definition. So let's go ahead and define this notation now. Okay, so let f and g be functions from the integers to the reals. Okay, so we say that f of x is big O of g of x if there exist constants say C and K, so that the absolute value of f of x is bounded from above, is less than or equal to C times the absolute value of g of x whenever x is greater than k. Okay, so this is what it means for f of x to be big O of g of x. Okay? And here, C and K, these are called the witnesses. When this definition is satisfied. So in order to show that a function is big O of another, you have to find these witnesses that satisfy this inequality. Okay, so what is this saying? It's saying that the magnitude of f as x gets bigger and bigger and bigger, because we're looking at x, all x greater than some value k. So the magnitude of x, right, is bounded above by some constant multiple of the magnitude of g. In other words, this function is not growing as another function times this one, right? So this constant multiple tells us that, in a sense, this function is behaving like that. It's bounded above by that function, okay? So let's just look at a plot real fast of this guy here. We'll call this f of x, or f of n, okay? And we'll call this g of n. Or no, I'll call it h. H of n. And I just want to look at what the graphs of those functions look like. So if I share my screen real fast, and then I pull up Spider, okay, so this is the standard plotting package in Python, matplot library. So it looks like, so def f of x is going to be return, let's say, 100 times x squared plus 17 times x plus 4. And then def h of x is just going to be x cubed. Okay. So in order to plot these things, I need a domain. So I'll just say domain is equal to the list range, say from 0 to 400, so it's a list of those things. So then I can do, so this is how I call the properties of pyplot from this library, and this is what you use to plot in Python. So I'm going to say plt.plot. So I give it the domain, and then I give it the function on that domain, and I'll give it a label saying this is 100x squared plus 17x plus 4. Okay, and then I'll do plt dot, domain. Domain, okay. dot.plot, domain, and then G on the domain. And then I'll give it the label. This is x cubed. All right, so if I just press Shift Enter, I run that. There is a error somewhere. Oh.
Professor, for line 15, do we should have to put like H domain or is it G domain?
What was that? I couldn't hear you.
For line 15,
Mm-hmm.
is it G domain or H domain?
Oh, H, sorry.
Yeah.
There's still an error here. Let's see. This shouldn't make a difference. I have an error somewhere, and I'm going to find it. This shouldn't make a difference. I'm just... One second. So backing up. F H. Oh, I might have not put a colon there earlier. F H. Interesting. So let me try something else real fast. I didn't want to use that library. Yeah. So basically the same thing. There was some weird error with the list that I had earlier. So this function here from NumPy, so NumPy is a numerical library. Arrange just makes a list from start to finish on intervals of that size. So you see start to finish, and then the intervals are of size 0.5. So it's just a bunch of numbers. The functions stay the same. So that's like our domain here. And then we apply f to domain at each of those points, and we get our function over here. Okay, so looking at these things here. All right, so we see that we have h and f. And if I didn't go to 500, if I went to like 100, or maybe 50. So here's H and here's F. It looks like F is growing faster, right? With this picture, it looks that way, right? So if our algorithm A is running on this many operations, and our algorithm B is running on this many operations, it looks like just from this picture that algorithm B is going to be better. However, if we keep on considering larger and larger input sizes, we see that around 110 or so, maybe, right around here, this function is bounding this one from above. You see that? So for large enough x, yeah, it's going to be the case that algorithm A is going to have fewer operations than algorithm B. Okay. So using big O notation, we would say that function f is big O of function h here, because eventually function h is going to be passing it at some point here. So it's just a visual way of seeing that what big O is trying to say. Okay, so let's look at an example of this stuff. So have this definition handy. We have witnesses C and K, so that f is bounded above by C times this function whenever x is big enough, whenever x is bigger than K. Okay. Okay, so let's look at an example. I'm going to say f of x equals to x squared plus 2x plus 1 is big O of x squared. All right, so we can prove this by showing that this satisfies the definition. So we just need to consider the absolute value of f of x, okay, which is equal to the absolute value of x squared plus 2x plus 1. So now, if x is greater than or equal to 0, then this quantity in the absolute value is going to be positive, so we can drop the absolute value in that case. But we have to make note of that over here on the side, and this is whenever x is greater or equal to 0. Okay? So now we need to somehow show that this is bounded above by a constant multiple of x squared. So what I'm going to notice now is that this is less than or equal to x squared plus 2 times x squared plus x squared whenever x is greater than or equal to 1. Right? Because, so here, if x is greater than or equal to 1, then x squared is greater than or equal to x, and then also x squared is greater than or equal to 1. So that's where this next line follows, and now we have like terms. So this is equal to 4x squared, and again, this is whenever x is greater than or equal to 1. And then finally, this is equal to 4 times the absolute value of x squared, just because they're equal. And again, whenever x is greater than or equal to 1. So here, we take c equal to 4 and k equal to 1. So the absolute value of f of x is bounded above by c times the absolute value of x squared, whenever x is greater than or equal to k, or greater than k. Okay? So one way that I like to think about this, that's not mentioned very often in textbooks, is that, so that's the end of the proof there, but just when you're looking at whether or not something is big O of another function, you want to ask yourself, how does x squared plus, was it 2x plus 1 behave for large x? So how does f, this function here, behave for large x? Well, imagine x is something like 2 to the power of billion, which is far more than the number of atoms there are in the universe. So 2 to the power of billion, that's a huge X, right? Does that term even matter anymore? If that number right there is big enough, right, the X squared is going to be so much larger. Like 2 to the power times 2 to the power of billion times 2 to the power of billion, which would be that term right there, is much larger than 2 times 2 to the power of billion. This means like nothing at that point. And that 1 definitely doesn't mean anything. So this thing basically is something like that for large, just emphasizing very large X. So you can get a sense of what that function is behaving like for large X just by considering what terms go away and what terms don't matter anymore when X is large enough. Okay. Okay, so let's look at showing something not being big O of another function. For example, n squared is not big O of n. Okay, so in order to prove this claim here, we can prove by way of contradiction. So maybe something like by way of contradiction, suppose it is, right? So suppose n squared is big O of n. So if it is big O of n, then there exist those witnesses, right? So then, by definition, there exists constants C and K so that the absolute value of n squared is bounded from above by C times the absolute value of n whenever n is larger than k, or greater than or equal to k. It doesn't matter which inequality you use. You can use strictly or you can use equal. It won't matter. It's the same definition. But the important thing to note here in this argument that we're using is that in that definition, these numbers C and K are constants. They don't change. Like they're fixed. And so notice that for n greater than or equal to k and n greater than or equal to 0, we have we can drop the absolute values, in other words. Right? So this inequality has to hold whenever n is greater than k. So this is like saying maybe, another way of saying this term here is for all, right? For all n greater than or equal to k, right? So eventually n is going to be bigger than 0, and bigger than k, right? Because we can just pick any n we want larger. So we can just keep on making n grow. But if this inequality holds and n is greater than or equal to 0, then it must also follow that if you divide both sides of this inequality by n, you get n is less than or equal to c. And again, that has to hold for all n greater than or equal to k and n greater than or equal to 0. Does anyone see a problem with this? Right there? Actually, I'll include the other piece. I just circled a problem. What is the problem? Anybody? Is it possible for this to be true in blue? I'm gonna wait. Someone has to see why this is a problem. If even up there, that blue is a hint, and then this blue is a hint, there's a problem. What's the problem? This right here is linked with this information here. Everything in blue is going to give you the problem. What is the problem?
Would that mean that k can also be equal to c?
Sometimes they can equal, but not always, right? The problem occurs what is c? What type of number is c? It's circled.
Constant?
It's constant. N is not constant. Right? For every n larger than k, right? So that means what? What does that mean about this inequality? Is it true or false? For example, what if c was 100 and k was like 4 or something? As an example. Then you would have what? N less than or equal to 100 for all n greater than or equal to 4. Is that true?
False.
It's false because why? Because n can be as big as we want it to be. Right? N can be 1,000. Is 1,000 less than or equal to 100? No. Because n is growing without bounds, that can't happen. So this is a contradiction. It's false. Because c is a constant, right? And under the assumption that n squared is big O of n, we have this inequality whenever n is greater than k. But when n is greater than k and n is greater than 0, which will happen eventually, we can drop the absolute values. We divide both sides by n, and we get that a variable that can grow without bound is bounded above by a constant. That's a contradiction. which means that if we assume this to be true, we get something false. So the original statement must be true. And that's the idea behind showing that it's not. That you get somehow that a number that can grow without bound is bounded above by some constant, and that can't happen. Okay. All right. So that finishes the proof. So let's look at another problem. Let f of n equal to 1 plus 2 plus dot 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 plus n. Give a big O estimate for f. So if this is our function, we want to find a big O estimate of this thing. So if we look at the absolute value of f of n, that's equal to the absolute value of 1 plus 2 plus dot 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 plus n. Okay. But this is always positive, so we can just drop the absolute values. Like that. Okay. Now here, this, so what can we say here? Again, we're trying to write an inequality here. Well, isn't it the case that, so n is the largest number out of all of these elements being summed here, right? So isn't it the case that that is less than or equal to n, that one's less than or equal to n, so forth and so on. What's that one? And how many n are there? There's n of them, right? So it's like n times n or n squared. So here we can take c is equal to 1 and k is equal to 1, and with these witnesses we see that this function f is big O of n squared. So summing the first n integers, positive integers, is big O of n squared. Okay. All right, so let's look at maybe another example. So let f of n be equal to n factorial now. So recall, n factorial is equal to n times n minus 1 times n minus 2 dot 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 times 2 times 1. And 0 factorial is defined as 1. Okay. So So if we look at wanting to find a big O estimate of that, well, we can drop the absolute values. The factorial is always positive. So that's equal to n times n minus 1 times n minus 2 times dot 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 times 2 times 1. But now, so this is less than or equal to, so n, they're the same, but n minus 1 is less than or equal to n. N minus 2 is less than or equal to n, dot, 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 all the way through. 2 is less than or equal to n, and 1 is less than or equal to n. So we get this upper bound here. How many n's are there? There's n of them, so n being multiplied n times. This will be equal to n to the power of n. Okay, which is the same thing as saying the absolute value of n to the power of n. So, if we take witnesses to be c is equal to 1 and k is equal to 1, we have n factorial is big O of n to the power of n. Okay? But notice here that if you pick up this piece here, there's an inequality right there, and then there's n to the power n. What we've just shown is that n factorial is less than or equal to n to the power of n. Now, from here, we can get another useful bound that you need when dealing with showing functions to be big O of another. So what we can do is from here, we can take the log on both sides. And the logarithm is monotonic increasing, so the inequality is still going to hold. And we can use properties of logarithms and bring that into the front. Remember, exponents come down as coefficients when you have a log. So not only have we shown that n factorial is big O of n to the power n, we've also shown that log of n factorial is big O of n log n. Okay. Okay. So there are some useful functions like n log n and log n that often will bound given operations in an algorithm. Okay. So let's look at these. So real quick, my mouse is not working. I just need to look at something real fast. Log. Forget, it's just np.log. Okay. All right. So let's say that it's going to take a second to make. So F1, F2. So I'll say this will be 2 to the power x. This will be x squared and then 3x will be x times np log of x. Okay. And then f4 x will just be x. And f5 with x will be just log of x. Okay. And then maybe we'll do one more, which will be a factorial. So how can I do this? So if x is equal to 0, return 1, else return f of 0 with x times x. It should do it for the factorial function. Okay. So we have factorial, exponential, polynomial, linear log, linear, and log. Okay, so let's do this. Definitely going to need to decrease the size here. So like, I don't know, 10 maybe. So then here we'll have f1, which is the function x factorial. So now we'll just copy that and then paste a bunch of times. 2, and that is 2 to the power x. 2 to the power x. And f3. This is x log x. Okay. What am I doing? F4 is just x. And then finally F5 is log x. Let's see if this runs. Yeah, factorial grew a little bit fast. It's maybe, yeah, 7 looks okay. All right, so here's our plot. So you can see the various growth rates here, where x factorial is exploding very fast. 2 to the power x is also growing very fast. So these are somehow like bounding all of the other basic functions from above. You have x log x in green, which is a little bit higher than just the function x, and then log x is below x. So this is kind of like the standard functions that you'll see when you're finding big O estimates of a given function in question. Okay. So there's just some more plotting for you to see plotting in Python. It's kind of not my favorite programming language to plot in, but it works. I prefer myself to use Julia. Some of you should look at that if you have a chance. Okay. So let's look at some theorems now. Okay. So theorem. If f1 of x is big O of G1 of X, and F2 of X is big O of G2 of X, then, so part A, so a lot of times when you're working with algorithms, you'll find that the number of operations or some type of composition of functions. So this following theorem is concerned with compositions such as addition. So F1 plus F2 of X is big O of the max in absolute value, G1 of X, G2 of X, again in absolute value. In part B, the product F1, F2 of X is big O of, I think it's the absolute value of the product. Let me make sure. No, it's just G1 of X times G2 of X. Okay, so I don't have enough space to prove both of them. I guess I'll just prove the second one here. The proof of part B. So, let C1, C2, K1, and K2 be a constant can be associated with F1 of X to G1 of X and F2 of X to G2 of X. I'm just kind of trying to make that first sentence as short as possible. So maybe I'll say, i.e. the absolute value of F1 of X is at most C1 times the absolute value of G1 of X whenever X is greater than K1, and the absolute value of F2 of X is at most C times the absolute, or C2 times G2 of X whenever X is greater than K2. Okay, so now with this we can see that, okay, so hence, if we look at the product, right, so 1, 2 of X in absolute value, that's equal to the absolute value of F1 of X times the absolute value of F2 of X, which is equal to the absolute value of F1 of X times the absolute value of F2 of X. So the absolute value of the product is the same as the product of the absolute values here. But now F1, right, is bounded above by C1 times G1 of X, right? And then F2 is bounded above by C2 times G2 of X. So what happens is that this is bounded above by C1 times the absolute value of G1 of x times C2 times the absolute value of G2 of x. Because that is less than or equal to that, and that's less than or equal to that. I'm running out of room here, so I'll say C times the absolute values of the product. And here C is equal to C1 times C2. That times that is C. And now the absolute value of G1 times the absolute value of G2, that's the same thing as saying C times G1 of x times G2 of x. But we forgot our K, so we'll say maybe, again, I ran out of room, but I'd say K is equal to the max of K1 and K2. So if x is greater than this, then x is greater than both of these, which means that it's x is greater than that and greater than that. So the C1 and C2 can hold right there. So that's just a short proof of part B. Kind of messy, but I'm running out of room. Yeah, so somewhere down there, you just say done. Okay, so let's look at another theorem. Okay, so theorem. F of x equals to an times x to the power n plus an minus 1 times x to the power n minus 1 plus dot 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 plus a1 times x1 plus a0. So that is a polynomial. That's a definition of a polynomial where an through a0 are just real numbers, and n is a positive integer. So this function here is big O of x to the power n. So if you have a polynomial of degree n, then that function is big O of x to the power n. Basically, all these other little pieces don't matter when you're looking at the growth. It's some constant multiple of xn will be larger than it. So the proof is not so bad. You just need to recall, so this is not a statement of the theorem. I'm just putting this is like a note. So triangle inequality is states that you sum if you sum x numbers in absolute value, that's at most the sum of the absolute values of those numbers. So that's the triangle inequality. So for example, like you sum a and b, that's less than or equal to the absolute value of a plus the absolute value of b. That's like a special case of that triangle inequality. So just that, you should always remember that triangle inequality is the absolute value of the sum is at most the sum of the absolute values. Okay. So with that, we can prove this theorem. So if we just look at the absolute value of this, we have this proof. This proof kind of takes a while to prove just because it's so long to write that thing out. So absolute value of that is equal to that. Well, by the triangle inequality, this is at most the absolute value of the pieces. And that's by the triangle inequality. And again, the absolute value of the sum is at most the sum of the absolute values. Okay, but now this is equal to so each piece we can write like this. I said this before. The absolute value of the product is equal to the product of the absolute values for each of these pieces. Okay. All right, so we're getting somewhere now. So if I had more room, I would write this, but I guess I'll write it over here. I'll say, let maybe A equal to the max absolute value of A sub I for I equal 1, through N. Oh, 0, because there's a 0, 1 over there. This one. So among all of those, this piece, right, so what I'm doing, I'm looking at, so that one, that one, that one, all the way through. I let A just be the maximum of all of those numbers. Those are all numbers, so I can say A is the maximum. So then this is less than or equal to A times that piece plus A times this piece plus dot 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 plus A times this piece there plus A. Okay. So now I want to say that now if x is greater than or equal to 1, then x to the power n is greater than or equal to x to the power n minus 1, which is, this will be the largest value for x whenever x is greater than or equal to 1 for each of these pieces. So then we can write another inequality and say, well, this stays the same, but now that is less than or equal to x to the power n plus dot 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 plus A, and now that is also less than or equal to x to the power n if x is greater than 1. And then this piece right here, there's like a 1 right there. That 1 is less than or equal to x to the power n. Again, if x is greater than or equal to 1. Okay, so how many of these pieces do we have? Well, we started with n plus 1, n including the x's, and then plus 1 for there. So altogether, this is equal to n plus 1 times A times x to the power n. So now if we take C equal to n plus 1 times A, but what was A? A was the maximum over all those coefficients. So max A sub I. And if we take k equal to 1, then we're done. Because then this is just c times the absolute value of x to the power n whenever x is greater than 1. So what that shows is that, yes, indeed, if you have a degree in polynomial, then that function is going to be big O of x to the power n. Okay. So that ends the proof there. I know it looks messy, but I'm sure if you just apply the triangle inequality, you just take that and that, and you write it on your own, it should make a little bit of sense as to why that's bounded above by that. Okay.
Excuse me, what chapters are going to be on the exam too? In the Rosen book,
In the Rosen book, it'll be 3.1, 3.2, and 3.3.
Okay, thank you.
Mm-hmm. So it's the section title is just in case the section numbers are different. The section title should be algorithms, the growth of functions, and then complexity of algorithms. All right. So that's the proof of that theorem. Okay, so that will be it for today's lecture. On Monday of next week, we're going to go over the rest of 3.2, the growth of functions. And then on Wednesday, we're going to go over complexity of algorithms. And then the following Monday, we'll have a review. And then Wednesday, I think I'll give you your exam to take home. So 2 weeks from today, I should post the exam on Blackboard. All right, that will be it. Everyone stay safe. And I will post this video to my YouTube channel as soon as it finishes rendering. All right, have a good day.